Thank you for this opportunity to speak this morning. It's been a good set of presentations so far, and I hope I don't drag the quality down from this point. So I'm going to quickly just give a little bit of background so you know where I'm coming from. I'll be talking about hydrogen vehicles, as Johan said. I'll do a little bit on the technology on board the vehicles, technology surrounding the refueling of the vehicles, factors affecting a technoeconomic assessment, and then some strengths, weaknesses, and opportunities and recommendations. So I'll just go through this, try and not lose too much time. So Change Energy is a small engineering consulting firm. We've been doing alternative transportation fuels between my main partner and I for the last 32 years, really specializing in compressed and liquefied gaseous fuel systems and solutions. Now, I want to stress we are fuel and technology neutral. We're not selling any particular kind of fuel or any particular technology. In fact, we're not a fan of anything except finding the right, the optimal solution for the end user. There's no point deploying an alternative or emerging fuel in an application for which it's not providing an optimal solution. We are concerned with the assessment, business case assessment, and then the design and implementation of refueling systems that yield the desired economic, environmental, and social outcomes. Our experience over the last 32 years has been international. We've built, or at least designed and been part of the project management of the construction of over 150 large gaseous vehicle refueling facilities, and also bulk fuel filling and decanting facilities for industrial applications of these fuels. We've spent about 15 years doing life cycle socioeconomic modeling of stations, fleets, and regional infrastructure. And we just completed a comprehensive supply demand delivery model for all of Ontario for hydrogen applications, looking at about 20 different hydrogen supply options, 5 different delivery options, and about 30 different end-use options for hydrogen across the province of Ontario. We've also spent about 30 years, I just got my 30-year certificate from CSA in the development of codes, standards, and regulations. We do a lot of work on the development of provincial and municipal regulations for the introduction of these fuels as well. So we do design of infrastructure, we do safety assessments and development of regulations, we do business case assessment, we do assessment of markets and applications, but we also do a lot of work on the development of end-use applications and the development of certification training courses for the personnel that will ultimately need to operate this equipment. So getting right into hydrogen, just a little bit about how fuel cell electric vehicles work. I apologize if this is beneath the knowledge level of a lot of the audience here. I'm sure it is, but nevertheless, fuel cell electric vehicles are powered by hydrogen, and in that process, they produce zero emissions. The hydrogen and oxygen combine within a fuel cell. Typically, there are hydrogen internal combustion engines out there as well, and blended systems, but just focusing on the fuel cell here, the hydrogen and oxygen combine to produce electricity. That electricity is directed to a motor or a battery system to power the vehicle. While the drive systems are electric, driving range is provided by the hydrogen on board the vehicle, not the batteries. Alternatively, as I mentioned, hydrogen can be used in ICEs much the same way as conventional hydrocarbon fuels, but with zero emissions, zero emissions, there's a Freudian slip, but with zero emissions, as long as the proper fuel stoichiometry and catalysts are used. The image here, and sorry that it's a light duty vehicle, it's just intended to give you an idea of the major components. So typically you will have a low voltage auxiliary battery that provides power to onboard systems. You have a high voltage battery pack, which stores energy generated from the fuel cell and the regen braking system and provides supplemental power to the electric traction motor. One of the main components, aside from the fuel cell itself, is the DC-DC converter, which is converts the high voltage DC from the fuel cell to the power the traction, to recharge the traction battery and to provide fuel electricity directly to the traction motors. Using power from the fuel cell and the traction battery pack, there is then an electric traction motor that drives the vehicle's wheels. Most vehicles use motor generators that perform both the drive and regen functions. The fuel cell stack is essentially an assembly of individual fuel cell membranes that combine oxygen and hydrogen to produce electricity and water. Much like a conventional vehicle, we have a fuel tank, in this case, a hydrogen fuel tank, which stores hydrogen gas, typically, or liquefied hydrogen on board the vehicle until it's needed by the fuel cell. Power electronics controller manages the flow of electricity, which is a multifaceted operation. And of course, then there's a thermal management system that maintains proper operating temperature of the fuel cell and the other components. When talking about fuel cell electric vehicles, we often get asked two questions very frequently. The first is, how safe is the fuel cell electric vehicle in the event of a collision? Well, of course, the tanks that contain the hydrogen are designed to rupture rather than, to prevent rupture. And they're designed to split and rupture rather than burst. That's what I'm getting at here, rather than burst. They're designed specifically so that they don't explode in a, you can't levy a gas fuel. You can levy a liquid fuel, but nevertheless, you don't want that tank to burst. They are designed specifically to rupture and release the gas rather than burst in the case of a substantial crash. The tanks also have relief valves, of course, that allow for managed venting if the tank were ever to become overpressurized. And in addition, if the hydrogen were to leak, the gas dissipates. In contrast, if you have a liquid fuel, such as gasoline leak, gasoline pools and creates a significant fire risk. In the case of a hydrogen tank, typically the hydrogen just releases and dissipates extremely quickly. It has a higher dissipation coefficient and higher buoyancy even than natural gas. So hydrogen, when released, tends to leave the scene pretty darn quickly. Ultimately, though, there are safety measures in place that allow for the safe and effective management of hydrogen in a vehicle. Second question that we get very often is, how do fuel cell electric vehicles perform in cold weather? Well, the long and short of it is that hydrogen vehicles don't see the same deterioration of range or overall performance that a battery electric vehicle typically does. That's not meant to slam battery electric vehicles. It's just saying that hydrogen as a gaseous fuel, we're not worried about vaporizing the fuel. We're not, and the fuel cell tends to operate extremely well across a very wide temperature range. Now, people worry about the water, seem to be concerned about the water exiting the tailpipe. But it's warm water, just as the main component of the exhaust from any internal combustion engine today, of course, is water. And the fuel cell, while it generates a little more water than a gasoline internal combustion engine does, and at a lower temperature, the dissipation of that water is not an issue. There are strategies to deal with the water that is inside the fuel cell. That technology was solved 20 years ago. Toyota has run several tests throughout the United States as well as in Canada. Yellowknife is a popular testing ground for Toyota to prove system performance.
Right, I just want to say that you have about 5 minutes left.
Okay, well, I'll skip through quickly then. The Advantages of utilizing fuel cells on a medium heavy duty vehicle are the potential for greater range on as an electric vehicle, quicker refueling times than battery electric vehicles, higher efficiency than diesel, better emissions, excellent emission reductions depending on the source of the hydrogen, noise reduction, lighter weight energy storage as a battery, an electric vehicle, and thereby permitting large payloads. The disadvantages are the cost. The costs, of course, are technology dependent, but currently the cost of hydrogen electric vehicles and hydrogen refueling is quite high. There is, of course, a lack of refueling facilities. You don't have as good range as you would with diesel. Better range than with battery, but not as good as with diesel. And the efficiency is not as good as the round trip efficiency is not as good as with battery electric. And of course, another disadvantage is the hydrogen supply chain is very immature at this point in time. There are no easy answers. The net benefit is case by case and depends on the value drivers of the investor end user. There are a number of heavy duty hydrogen electric vehicles available today. This is just a couple of them. There's the Hyzon Class 8 and the Hyzon Hymax. I'm assuming these slides will be available afterwards so you can look at the specifications at your leisure. But Class 8 hydrogen tractor trailers are available. I mention and display the Hyzon, but there are a few others that are out there as well. Nikola, of course. Hyliion is intending to come out very soon, and I have a much more comprehensive list. If you're interested, I can provide that to you at another time. There's also the opportunity to do vehicle retrofits and the use of hydrogen internal combustion engines. The restrictions on internal combustion engines are being lifted for internal combustion engines that run on renewable or zero emission life cycle fuels. So in the EU and China, right now they are recognizing hydrogen. The fuel itself is when you're using a retrofit or an ICE, you can use lower grade, less expensive hydrogen. Of course, that creates complexity at refueling facilities. The cost of the vehicle is much less than the cost of a fuel cell when you're running a hydrogen ICE. The availability, hydrogen ICEs have been around for quite a while. BMW, Ford, and Aston Martin have developed these. And unfortunately, though, they're just entering commercial availability in a limited range of markets. And blending so not a 100% hydrogen ICE, but blended applications are also available. There are a few companies that do combination or blended fuel applications. In Canada, Hydra Energy out in BC is probably the leader of the pack there. When we look at refueling, there are a lot of challenges. When we think about refueling in practical, we really have to focus on pressure and fill type. Hydrogen has great energy density on a mass basis, but its volumetric density is kind of lousy. At 350 bar, we're at a compression ratio of 230 to 1, but this still means that the volume taken up by hydrogen is about 6.3 times the volume that an equivalent amount of diesel would take. And that's even when you take hydrogen's higher energy efficiency into account. Hydrogen through a fuel cell is around 50% efficient, whereas diesel is only 30% efficient, give or take. Even taking that efficiency change difference into account, you're looking at that kind of volumetric requirement for range. At 700 bar, that translates to a 3.4 times volume, but of course 700 bar is a lot more expensive and more difficult to work with. Hydrogen can also be liquefied, and now we're getting a little bit better. We're down to around twice the volume that diesel would take when you're using liquefied hydrogen. However, liquefying hydrogen requires cooling it down to minus 252 degrees C, which creates new capital cost and operational costs. One of the operational issues is the fact that it boils off. So all in all, liquefied hydrogen is generally more suitable for heavy duty long haul vehicles that operate on a 24/7 schedule or something close to it. So long haul heavy duty tractor trailers are a good application for liquefied hydrogen. I mentioned the 3 types of fill station. These have a dramatic impact on the cost of the station, whether you're using a slow fill, a fast cascade fill, or a fast buffer fill. I don't really have time to get into that in a lot of detail, but that needs to go into your modeling. The standard equipment includes both the source of hydrogen, what's referred to as a deoxo dryer to purify the hydrogen, a compressor, filtration systems to get you down to 99.9995% purity of your hydrogen, storage systems, chilling systems. And then you have a variety of dispenser options and dispensing approaches, strategies that need to be taken into account. And these all have serious impact on the cost of your station. And so those things need to be built into a techno-economic assessment model. I've mentioned the benefits of liquefied hydrogen and the various components on site for a liquefied hydrogen fueling facility. You have the addition of a storage tank, vaporization systems, the cryogenic pump, and a cryogenic dispenser. Value drivers, I'll just skip over this. I know I'm out of time here, so I'll just jump to some of the factors. The techno-economic assessment modeling we do is highly granular and comprehensive, featuring there's a wide range of key variables that need to be addressed. And here, this is a very high-level partial list of some of the typical factors that we would consider, including design and regulatory factors, capital cost factors, operating cost factors, operational viability factors. And then, of course, you have to take into account non-monetary drivers as well. Does the end-use customer care about greenhouse gas emission reductions and other opportunities for deriving revenue and moving down costs? So there are a number of these other factors that need to be built into a model to get a good picture of what the viability of hydrogen as a vehicle fuel is. So just some really high level SWOT topics and recommendations. You have to consider both market ready and emerging technologies. And unfortunately, we're in a state where hydrogen technology is rapidly evolving and improving. And that actually hinders market adoption because people always want to wait for the best technology. And that is always just around the corner. Tomorrow never comes. You have to rigorously identify and define the goals of the end use community. Do they want costs reductions, minimizing costs? Do they want to minimize emissions? Are they more focused on job creation and other social benefits? And you really have to weigh those key performance indicators, and they must be built into any truly complete techno-economic assessment model. You have to recognize that government funding skews the playing field, often engendering the wrong and ultimately unsustainable markets. And that was certainly the case with the great experiments with natural gas vehicles in the 1990s. Having the government funding applied to the wrong markets really undermined the development of natural gas as a vehicle fuel. And that's just a historical fact.
Hi, Ryan, I'm just going to have to ask you to wrap up.
Yep, funding strategies have to evolve from technology development to demonstrations to market development, and that's where things begin to get tough. And then ultimately, they have to be designed around ultimately having no funding available, so you have a sustainable market. And we have to proactively address market barriers such as safety regulations and end user familiarity and avoid siloing. Hydrogen is just part of an overall energy infrastructure and energy system, and it has to be viewed within that wider energy system not as a standalone technology. Sorry, I went a little bit over there.
There's a lot of info. It's more challenging to do less time than more. But
Yeah.
the PowerPoints are all going to be available online. So everyone that will participate in the roundtable can go, if they want, look into this. Lots of great information. And of course, if you want, contact Rye for more info at some other point. So the next speaker is going to talk to us about natural renewable gas trucks. It's Francisco Doyon, who is with Énergir, like I said, the natural gas distributor. So there you go. Francisco, the floor is yours.
Very good. I'll just start my camera. So first, thanks a lot for having me, Joanne, and the HSA. It's great to be here and to contribute to the discussion today. My name is Francisco Doyon. I'm an advisor for the development of natural gas for vehicles, or NGV, at Énergir. Énergir, for those who might not know us, we're the main natural gas utility here in Quebec. And we also have a diversified portfolio in the production of renewable energies, such as electricity with assets in hydro, wind, solar. And we recently announced our involvement in the production of renewable natural gas, RNG, here in Quebec. Today, I was asked to provide you with a quick overview of how renewable natural gas can be used as a decarbonization tool for long-haul trucking, and more specifically along the corridor separating Windsor to Quebec City. As you'll see through the next couple of minutes, what I'm talking about here today is a technology that is ready to hit the ground running, with a refueling infrastructure that is already in place and continues to grow, an increasing supply of renewable natural gas available today and in the future, trucks that can be ordered today from established truck OEMs and benefit from the existing support and maintenance network that is in place, which is required by a fleet to move with confidence and minimize the impact on their operations. To do so, I'll first go over a few basic concepts to explain what exactly is renewable natural gas and how it is considered as a fuel with a net zero carbon footprint. Then I'll cover aspects relating to the fueling infrastructure, the performance and availability of the technology for trucks. And finally, I'll go over a few pros and cons on the RNG solution with recommendations for the future. So renewable natural gas is renewable energy and can come from various streams of organic residues such as household, commercial waste, agricultural waste, and sewage treatment plant sludge. Those residues are collected and sent to a biomethanation plant where, in the absence of oxygen, microorganisms decompose the material and generate methane-rich biogas. After cleaning and purifying this biogas, we obtain biomethane, or renewable natural gas, RNG, that has the exact same specs as traditional natural gas in order to be injected in the existing pipeline network and is therefore totally interchangeable. As the renewable natural gas molecule is injected by a producer into the pipeline network, it becomes impossible to differentiate it from a traditional natural gas molecule. As such, the consumption of RNG is done on an accounting basis, and customer has to opt in voluntarily to purchase the RNG from Énergir here in Quebec, for example. By paying the premium price of RNG, the customer also acquires the green attributes associated with it, or the GHG reductions. It's important to understand that a customer purchasing RNG, for example, a refueling station, will not physically consume the RNG molecule that he's buying, but will instead be acquiring the volumes that have been injected by an RNG producer. I often like to use this analogy to illustrate the transaction of RNG. So let's say that I'm in Quebec City and I take out of my wallet a $20 bill and go to deposit it into my account in an ATM. I then travel all the way to Windsor and withdraw a $20 bill from another ATM. So that $20 I just withdrew is without any doubt my property and is mine. However, the physical bill I'm holding in my hands is not the exact same as the one I deposited in Quebec. So the same can be said for renewable natural gas and how it is accounted for. For this reason, Énergir has a stringent auditing process in place and rules which are overseen by the Régie de l'Énergie to ensure that we have secured the supply of every molecule of RNG that is then sold on to our customers. For 2030, the government of Quebec has set a target for Énergir to inject 10% of renewable natural gas of the total volumes that we distribute. We're on good track to achieve this goal, and we also have the ambition to exceed it. The provincial government also supports through the Plan for a Green Economy the production of biofuels such as RNG with an envelope of over $200 million. RNG is considered a carbon neutral fuel because its life cycle carbon intensity is close to zero, and for certain organic inputs can produce a negative CI. The use of RNG also contributes to a circular economy, can be produced locally, ensuring a stronger energy autonomy. As far as availability, it can be purchased today, and there's a growing supply. Today, there's more than 280 operational RNG production facilities in Canada and in the US combined, and there's more than 475 that are either under construction or planned. So a lot of RNG coming our way. So now moving back to the use of RNG in trucks for long-haul applications. So we've established where RNG is coming from, how it is distributed to an end customer through the pipeline network. So let's look at the infrastructure for refueling trucks. On board a heavy-duty truck, there are two ways to store natural gas. It is either compressed, CNG, or liquefied, LNG. LNG will roughly require half the volume of CNG cylinders to achieve the same autonomy. In the recent years, with improvements in CNG tanks performance and weight, CNG has taken the lead as a storage method for onboard fuel on trucks. It is simpler to refuel, no certification is required, and the CNG stations are directly connected to the natural gas pipeline infrastructure, ensuring a steady and reliable supply. For this reason, I'll focus on CNG for the next few minutes. For those who might have never seen a compressed natural gas station, this is what it looks like in a nutshell. So after the utility meter set, you have a dryer, compressors, storage tank, and a fuel dispenser. The natural gas is compressed at 3,600 PSI on board of the CNG tanks that are on the vehicle. And the refueling is done in public stations as fast as refueling diesel in 5 to 10 minutes. There are more than 640 CNG public stations already in place in Canada and in the US that are accessible for heavy-duty trucks. 25 of those stations are located in Canada. More specifically, in the corridor which we're looking at between Quebec and Windsor, there are 13 stations, and the longest distance between two being 250 kilometers. Just keep in mind that the average autonomy of a CNG truck is about 900 kilometers. In Quebec, all the CNG stations have access to sourcing renewable natural gas directly from Énergir. And in Ontario, CNG stations can also source RNG through Enbridge. To summarize, there's already an existing infrastructure in place which can supply renewable natural gas to heavy-duty trucks, and the solution is readily available for fleets today. There's no piloting required here. This is ready to go now with the right support to freight carriers. So now moving on to trucks technology and performance. When using natural gas to power a truck today in North America, there's currently one engine manufacturer called Cummins that offers the internal combustion engine that uses 100% natural gas. Cummins is one of the largest engine manufacturers, and its natural gas engine technology has been around for more than 30 years and keeps on evolving. Compared to a diesel engine that ignites by compression, the natural gas engine is spark ignited, similar to a gasoline car. And in terms of pollutant emission, this engine is much more cleaner than diesel, and they do not require diesel particulate filter, which has become an increasing headache for fleets operators and reduces uptime. There are currently 3 sizes of engine commercially available today. For the long distance tractor application we're talking about here today, the 12-liter engine with 400 horsepower is the most appropriate tool that is available today. As far as maintenance on a natural gas engine, it's different than from a diesel engine. However, the maintenance costs are conservatively considered to be the same. Fleet feedback in some instances is that it can be significantly lower. The natural gas engine performs very well in cold weather application. This has extensively been demonstrated by many fleets here in Quebec and in Canada for many years now. With the arrival in 2024 of the 15-liter engine from Cummins with 500 horsepower, will open up many 3 to 4 axles applications, so heavier loads, which are common here in Quebec and Canada, which were limited in the past with the use of the 12-liter engine. On this new engine, improvements have been announced by Cummins in terms of efficiency and emissions reduction. There's continuous R&D done on those engines that already meet the standards for EPA and CARB emissions for 2024 and 2027. In terms of range and autonomy of those vehicles, depending on the desired configuration of CNG tanks, be it lateral, back of cab or combination, and operational limitations such as wheelbase for a day cab or a sleeper configuration, you can install lateral tanks up to 120 DGE or diesel gallon equivalent for 2 rail mounted tanks. And for the back of cab package, you can go up to 175 DGE. So for a reference, the back of cab package, the 175 DGE will provide a conservative autonomy of 900 kilometers for a truck. For a sleeper configuration using a combination of lateral and back of cab tanks, you could go as much as 295 DGE, which represents a range of 1,600 kilometers. The added weight on a CNG trucks represents roughly an average of 400 to 500 pounds compared to a diesel truck, with a marginal impact on total payload. So all major OEMs that you see here on the screen, Freightliner, Kenworth, Peterbilt, Volvo, Mack, offer the integration of the natural gas engines in their chassis. The truck is assembled by the OEM with the natural gas engine directly on the production line and goes on to be delivered through the existing truck dealerships all across North America. So if we look now at an example that would represent a typical use case for a truck traveling between Quebec City and Windsor, day cab truck equipped with the back of cab tank package that I described earlier will carry an incremental cost of approximately $90,000 compared to its diesel equivalent. Considering the Éco-Camionnage grant of 30%, the net incremental cost would be roughly $63,000. Taking the price of diesel for the last month, published by the Régie de l'Énergie, a trip from Quebec to Windsor would cost approximately $680 for the diesel only. For running the exact same route using renewable compressed natural gas, the fuel bill will be $490 or 25% less than diesel. So considering a yearly mileage of 150,000 kilometers, those fuel savings would allow to recuperate the incremental cost in 2.6 years and would yield reductions of emission of about 145 tons of CO2 every year. So here I've got a SWOT. There's many items that I've covered in the strength specifically, so I'll focus on the other categories. There's a lot of items. I'll leave you to read them after, but I'd like to focus on one of the weaknesses. It's that we need actually more maintenance shop that are required and more technicians to support those CNG trucks wherever they might go. This hinders adoption in many cases because fleets will operate different routes and they need access to the service to have the truck up and running. As far as the opportunities, what we see is that many companies are defining ESG and emissions reduction targets. Those companies are putting pressure on the carriers they work with to come up with emissions reductions while maintaining competitive pricing, and that is good for all alternative fuels. Finally, a threat that I'd like to highlight is more specifically for the third-party logistic operator. The current pricing model working with the fuel surcharge for diesel puts the alternative fuels, so renewable compressed natural gas, for example, at a disadvantage. So this has to be considered into the whole process of transitioning and adoption. In terms of recommendation, so there's a lot of focus on zero emission vehicles for battery hydrogen vehicles, for example, to establish objectives or mandates for the OEM. We think that a life cycle approach should be taken and that renewable natural gas should be considered at the same level as those technologies, since it's delivering significant emissions reduction at an interesting cost. Second, incentives are already in place through Éco-Camionnage to support the fleets when purchasing natural gas trucks. Those incentives are important to maintain, and it would be a good idea to explore extending that coverage when using renewable natural gas. By doing so, it would reduce the upfront capital costs for the truck purchase and would yield an interesting return in terms of dollars per avoided ton of GHG. Finally, the two last, so continue to support the deployment of more public CNG infrastructure to open new corridors to increase refueling opportunities for fleet and the access to renewable natural gas. And finally, support truck dealerships, heavy-duty maintenance repair shop to upgrade their infrastructure to service compressed natural gas trucks and all the alternative fuels that will be part of the future. So thank you very much. If you have any questions, here's my contact info, so do not hesitate to reach out. Thanks.
Merci, Francisco. There's actually a question that was asked about, I guess, the potential and realistically how much supply would be available for renewable natural gas, not just natural gas between Canada, US. So maybe you can answer that. I think somebody answered it, but you can provide also an answer if you want. So our next guest is going to be David Cebon from the University of Cambridge that will present us on the catenary trucks. David, if you can share your screen.
Thanks, Joanne. Sure, just be 1 second. Just got to find it now. It's disappeared. Here it is. Okay.
Yeah, there's a green button. I think you can.
Yeah, no, it's my presentation I have to find. Good. I hope that that is now on the screen.
You can expand it.
Yeah, is it okay?
Yeah, perfect. Thanks.
Great. Thank you very much. It's a great pleasure and privilege. Thank you for inviting me, Joanne. Great to be here. I'm just going to talk about electrification of the long haul freight in general and give a bit of a UK perspective on this. And I want to talk about big batteries compared to electric roads or dynamic charging. And I'll draw some conclusions. So if we think about the options for decarbonizing long haul, we've got big trucks with big batteries like the Tesla. We've got dynamic charging, electric road systems, which I'll talk about. There's hydrogen fuel cells we've heard about. There's battery or tractor swapping, and these are similar, not quite the same. They have different, slightly different dynamics, but they're important to consider. There's hybridization, which hasn't been discussed here. And I think ultimately hybridization is probably the answer for long haul. And there's biofuels, which we've just heard about, which all the calculations I've done on biofuels indicates that there's not nearly enough to go around. And it's not a solution for decarbonizing the large mass of vehicles. And in fact, we need those precious biofuels to use for aviation and shipping. So I'm going to talk about the first three of these. If we think about electrifying the long haul, much long haul freight goes between distribution centers and consolidation centers. This is a little schematic of the UK network showing a network of backbone network of highways connecting cities and distribution centers. And it is possible to run along this backbone network with catenary trucks, overhead contact lines. These trucks pick up their power from the contact lines. It goes straight through an inverter into the traction motor. Some can be used to charge the battery at the same time. And these vehicles typically have a significant size of battery, much smaller than a big battery vehicle, but significant size, a couple of 100 kilowatt hours. And that enables them to drive 50 miles or more from the end of the from motorway junction, from the end of the contact lines to their distribution center or whatever. So I'm going to talk about that. It's a very attractive technology. The design of a network is a bit of a challenge, and I'm going to give you an example from the UK. And I would point out that I think that there's a bit of a challenge in this study that you are undertaking, Johan, which is that it's just considering one road, whereas the freight decarbonisation problem is a system problem, and you really need to think about the whole system, not just one road, the whole country. And I'll show you a little example of that here. So we've been thinking about the design of electric roads in the UK. And of course, the first thing that you discover is that when you get to the end of the line, the contact line, you've got an area of operation where you have to be able to run on the battery. And quite likely you're going to need some static charging in that area. And that is going to be all around the country. So you're going to need static chargers, as shown here, in various places. They will be in some truck stops, places like that, and also at warehouses. So we've investigated a number of different configurations of electric roads, but with static chargers. And you can see the black dots around here are static chargers. The blue are the light, medium, and heavy assumptions for the amount of electric roads. And let me show you some results for one real operation. Now, this is an operation that the map shows you the bottom of the UK. We've got London here. I don't know if you can see my cursor, but I'm showing my cursor. This particular vehicle, this is a real live day in the life of a truck. It starts at the red triangle here. It goes out to the west, drops off out of the blue triangle at the end, comes back, has a rest stop at the next blue triangle, comes back to the depot, goes back down south, down near to the Isle of Wight there, and then comes back again, and then goes all the way up around London and comes back again. And that is one real journey in the life of this truck. Now, if the truck, you try to do this journey using just a big battery with no charging anywhere along the line, you would need 1,666 kilowatt hours of battery. That's 1.7 megawatt hours of battery, which is about 1 megawatt hour bigger than any manufacturer is currently making. If you charge the vehicle at the drop-off sites, that is the 3 blue triangles at the ends of the lines, you would need 397 kilowatt hours of battery. That is a much more practical battery size, but it needs chargers, fast chargers at the ends of the line where the vehicle stops for about a half an hour before turning around. And during that half an hour, while it's being loaded or unloaded, you can charge with a fast charger, and then you'd only need about 397 kilowatt hours of battery. If you charge at the public rest stops in UK and Europe, truck drivers are forced to take a rest at 4.5 hours for 45 minutes. It's a statutory rest break. That's what goes on at these 2 little triangles here. And if you use that 45 minutes to charge, but you don't charge at the ends of the line, then you need 800 kilowatt hour battery, because to drive this 44-ton truck for 4.5 hours needs 800 kilowatt hours of battery. And you can charge at both the stop-off points and the rest stops. Doesn't make very much difference to just the stop-off points, because it really depends on the scheduling that goes on. Now, suppose you added the light ERS. And you can see the light ERS is the blue, little sort of blue lines, cyan lines. And in this case, you can see there's so part of the light ERS goes around what's called the M25, the London Circular Motorway, orbital motorway. And what you can see happens here now is that the no static charging case reduces to 1,000 kilowatt hours, and the drop-off case decreases to 250 kilowatt hours, 40 kilowatt hours, which is the size of a battery in a bus. Doesn't make much difference to the public rest stop case, because that case is dominated by the early part of the drive cycle when the vehicle drives for 4.5 hours between these rest stops, and so it doesn't make any difference to that. If we go to the light or heavy ERS solutions, let's just go straight to the heavy one, you can see that the battery sizes come down dramatically. Now, instead of a 1.7 megawatt hour battery, which we needed to start with, we only need a 220 kilowatt hour battery, even if we have no static charging at all. If we have static charging at the drop-off points, now our battery is down to the size of a Tesla car battery, 80 kilowatt hours. So you can see that the effect of the ERS is to dramatically reduce battery sizes. That means dramatically reducing the weight of the batteries and the cost of the batteries, the carbon footprint of the batteries, the critical materials used by the batteries, and of course the carbon footprint of the vehicle, which is critically dependent on its weight. A lightweight vehicle uses a lot less energy to transport freight than a heavy vehicle. So if we look at the distribution of battery sizes needed for these light, medium, and heavy cases in the UK, and we've simulated tens of thousands of real logistics journeys in the UK using this same methodology. And what you can see is that with no ERS, the mean battery size we need to do all UK logistics is 600 kilowatt hours, but there are some batteries that would need to be up to 1.1 megawatt hours. That's a very big battery. If we have the light ERS, that goes down so that 90% of vehicles have less than 600 kilowatt hours, and the mean is down at 300 kilowatt hours. That makes a big difference. If we include static charging, destination charging as well, then the blue one doesn't change, but now the mean comes down to 150 kilowatt hours, which is a small battery, and the 90% of all vehicles have less than 300 kilowatt hour batteries, which is small bus size battery, which doesn't affect the payload of the vehicle at all if you're down to that size. Let me just make some comments on hydrogen powered vehicles. This is what happens when you take renewable electricity, you transmit it by the electricity grid, convert it from AC to DC, and you put it into a battery electric vehicle. If you start with 100 kilowatt hours of renewable electricity, you get about 70 kilowatt hours at the wheels of the vehicle, taking account of all these inefficiencies. So you lose 30% of the energy that you generated as heat in the transmission and conversion process. If you take that same 100 kilowatt hours of electricity and make hydrogen from it, the electrolysis process is about 75% efficient at best. You take that hydrogen, you compress it and transport it. You put it in a fuel cell, which is 50% efficient at absolutely best, as governed by the second law of thermodynamics, and then put it in an electric vehicle. You find that about 23 or 25 kilowatt hours actually makes it to the wheels of the vehicle. So of the 100 kilowatt hours we started with, we've thrown away 75% of the energy in going through these conversions from electricity to hydrogen and back to electricity again. Now that 75% of energy has to be paid for, it has to be generated and has to be paid for. And that means that the 25% left over at the end is very expensive. If we do the same thing with ERS, we go through the same process with ERS, we find that 77 kilowatt hours gets to the vehicle at the end. And the reason that that's better than the battery electric vehicle is that you don't have to go in and out of the battery, and you don't have that round trip inefficiency of the battery charging and discharging, which loses some of the energy. If we take these efficiencies and the amount of road freight that gets shipped in the UK, and we estimate how much renewable electricity would be needed, then this is what comes out. If you were to use the electric road system for all UK road freight, you would need about 10.6 gigawatts of electricity. That's about 3,500. If you put it on land, if you did land-based wind turbines, it's about 3,500 wind turbines, a land area of about 5,000 square kilometers. And that's shown to scale as a circle on the map. If you did the same thing with green hydrogen, you would need about 3.3 times more electricity, and you'd need 3.3 times more generating capacity, 3.3 times more maintenance, 3.3 times more little substations, 3.3 times more spare parts, 3.3 times more everything. The electricity will cost 3.3 times more to power the same vehicle fleet. That amount of electricity is about 36 gigawatts. That compares to the UK's average consumption through the year of about 31 gigawatts. So we have to double the size of the UK's electricity grid on average, the average consumption, in order to power trucks by green hydrogen. It would take the area shown to scale as about as big as Wales and Yorkshire put together on this. And clearly that's not a practical thing. If it was offshore wind, it could be offshore wind, it would still take 3.3 times more offshore wind to power the green hydrogen truck. The green hydrogen truck is going to be 3.3 times the cost of the electric truck to run. So hydrogen is 3 times at least the energy cost. Hydrogen-powered fuel cell vehicles are at least double the cost of battery electric vehicles. There's questionable decarbonization because of the huge amount of renewable electricity required will prevent the decarbonization of all other aspects of industry. The charging infrastructure, there are severe problems with getting hydrogen to filling stations, which nobody tells you about. And the availability of vehicles is questionable, with number of hydrogen vehicles manufacturers being in trouble and none available in the European market at the moment. Here's a total, our estimate of the total cost of ownership of various types of vehicles over a 6-year first life of a vehicle from 2030 onwards. Horizontal line is a diesel internal combustion engine vehicle, about £400,000 to purchase that vehicle and fuel it for 6 years before you sell it on. A fuel cell electric vehicle, we think that by about 2030, best estimates, will be about £560,000, which is about $800,000 to purchase and run for its 6-year first life. If we look at a 1.2 megawatt hour battery electric vehicle, it's unlikely to catch up with the diesel ICE even by 2050. If we go to the ERS vehicles with increasing amounts or decreasing amounts of battery and more ERS, what we can see is that they rapidly go below the cost of diesel in the early 2030s. If the cost of these vehicles is above the diesel line, then it's very likely the government will have to subsidize that because otherwise road freight will be substantially more expensive. On the other hand, if the lines here are below the diesel line, that provides government with significant headroom for taxation. And that's important because government currently gets a lot of tax from diesel fuel tax, and needs to find a way to pay that back, to generate that income. So revenue ability to tax is pretty important. Big batteries are simple and intuitive as a system, and no government intervention is needed. But they're very high cost, vehicles are high cost, there's a substantial loss of payload, and they're bad for mass limited loads. If you really want to carry the full 80,000 pounds on your Class 8 truck, which is not very much, it's only 36-ton truck, we carry 44 tons in the UK. if you want to carry your full 36 tons, you've got a significant problem if you've got to carry 6 or more tons of batteries on that vehicle. Warehouse charging, as you've seen from my example, warehouse charging is essential in this if you don't have ERS. Because if you don't have warehouse charging, you have to have huge batteries involved or significant delays charging them while you wait at the side of the road at a truck stop. Further to the point is that as we go to automated freight handling and to autonomous vehicles, both of those things will eliminate the times that are available for heavy vehicles to charge at truck stops. Autonomous vehicles don't need to stop at truck stops, and at warehouses, because we can now load and unload trucks, whole trucks, in a couple of minutes using automated warehousing systems. Both of those things take away the times in the logistics day when it's possible to charge battery electric vehicles. If you use ERS, you have the lowest cost vehicles, the highest payload vehicles. They're excellent for mass limited loads because they're lighter than diesels. They have the minimum energy consumption of all, the minimum carbon consumption, and the smallest batteries. Their benefits are enhanced by automation and autonomy because they can operate without having to stop at warehouses and without having to stop at truck stops. They just charge on the line while they're in motion. They need minimal warehouse charging, and warehouse charging is a big deal because putting a large fast charging array in a warehouse requires a big fat electricity connection, grid connection, and those grid connections, which may be 10 or 20 megawatts, they're very expensive and very complex and time consuming to install. So warehouse charging, which is needed by big battery vehicles, that is a significant problem, and particularly installation of grid connections in thousands of warehouses around the country. Finally, ERS dynamic charging is privately financeable, and we've done a lot of calculations of the finance by selling electricity on the lines. As long as you have enough truck traffic, by selling electricity, you can pay off the capital cost of the installation. So the cons for dynamic charging is that it requires government support. It doesn't require subsidies because it can be privately financed, but it requires government support in the form of, like any big infrastructure project, where you've got to ensure some income for the investors early on in the life of the project before the infrastructure has been constructed. And it requires highway authorities to learn about electricity, and I'm sure they can manage that. And so it also doesn't look nice. At least
wrap up in a couple of minutes, please. Yep.
Some people think it doesn't look nice. I think it looks great, like wind turbines. So electrification is all about the charging. It's nothing to do with the vehicles and fitting the charging into the logistics day. That's the critical problem of electrification. Automation will make charging significantly more difficult in future. For long haul vehicles, battery electric vehicles with dynamic charging, ERS, is the lowest cost, lowest carbon, and lowest mass way to go. Hydrogen is too expensive in capital cost and in operating cost. Electric logistics can be made to work. We've certainly demonstrated that in the UK. But logistics is a system, and I would have to say that I think there's questionable benefit of analysing a single route in isolation. You really need to understand that route within the context of all the vehicles that are coming onto it, where they're coming from, how they get to that route, where they go to, how they charge in other places around the country. And those things are really important if you want to understand whether the system will work or not. And so I strongly encourage you, Joanne and others involved in the study, to think carefully about the overall logistics system and not just your one highway. Thanks. That's all I had to say. I'm sorry for going a bit long.
Thank you so much. So our final presenter for this session is going to be Charles Trudel, who's going to talk about the battery electric trucks. Charles is with the Innovative Vehicle Institute. Charles, if you can present. Thank you.
Sure. Well, let me just put that full screen. Won't be long.
It's full
Here I
screen.
am.
That's good.
It is. All right. Well, thanks, Joanne. Let me start my timer. So first, let me thank you all for these wonderful presentations so far. I hope that you like the content so far, and I really look forward to share with you guys with the roundtables that are coming up this week. So I will provide you for the next 15 minutes a really high level, so 10,000 foot high overview of battery electric trucks as an option to decarbonize long-haul trucking in Eastern Canada. I'm Charles. I'm from the Innovative Vehicle Institute, IVI for short. We are, just to provide a bit of background first. Oops, sorry for that. Yeah, so just to provide a bit of background first before we dig further into battery electric trucks. IVI is a research center that's been dedicated to EVs and autonomous vehicles for the past 25 years. So for more than 2 decades, we were involved in the R&D projects. So we are behind most of the product developments that came out of the province of Quebec in the last decades. Namely, we are behind the first prototypes for Lion Electric, which were school buses at the time. And Lion Electric is now publicly traded. It's a big success story for us. So we are behind the first units of this company. We are also behind the Nova Bus Transit Bus, electrified transit bus, which recently received the 2.2 billion funding for more than 1,000 units of these electric transit buses that we helped to put together in our shop. So R&D projects are at the core, but we also have in our mission to help end users adopt new technologies around vehicles, so namely EVs. So we also, on the side, do fleet deployment projects for the first units of new technologies. Namely, we've been involved in a 4-year-long project for EV taxis, a 2-year-long project for EVs in driving schools, and 9 months long project for the first patrol car of the province of Quebec that's electric. And so you get the scheme. We want to be there to support the adoption of the first units of new technologies. So with that context, we are currently working on 3 years large-scale demonstration projects for Class 6 to Class 8 battery electric heavy-duty trucks. So the emphasis is on regional haul, but still I want to talk about it a bit because most of our knowledge base today and the knowledge that I'll share with you for the next minutes comes from this project that we call the Plug-in Fleet project. So we put the emphasis on 160 radius with a return to base application, so regional haul. Why? Because it is what the battery electric truck technologies allows for today. So it represents what fleets can buy and receive next year. So yeah, through this project, our goal is really to it's an information project, a demonstration project. So we go through different phases to inform the biggest number of fleet operators that we can in the province of Quebec. We organized events where there were ride and drives for 5 battery electric trucks. Then we measured the operations for 30 fleets across Quebec to really understand who are concerned today by electric trucks that are working today. So yes, again, original haul mostly. And in the end, in that project, we'll starting in this month of June, so this summer, we'll land over trucks, one electric truck for 1 month with a 50 kilowatt charger for free for 5 different fleets. So that's coming starting June. So jumping into battery electric trucks, a bit of your overview on the state of the local market in the province of Quebec. So as of December 2022, 70 battery electric trucks are registered in the province. Mostly are used for a less than truckload, regional haul, road work, third-party logistics. So yes, regional haul. one big advantage of the battery electric trucks is that all major legacy truck manufacturers now offer electric trucks. In our project, we have partnered with Peterbilt, Volvo, Freightliner, International Navistar, Lion. So most of the brands that fleet operators are already accustomed to, and some of them have been in business with for over centuries sometimes. So it's really impressive, the strong bonds between the OEMs, the legacy manufacturers, and the fleet operators. So I see that personally as an asset for the battery electric trucks technologies. It's not newcomers or new technologies to adopt as far as the business is concerned. So just to give you a bit of context, the early movers in Quebec have been operating 1 or 2 electric trucks for about a year. We are roughly 3 years behind California in terms of project sizes and involvement levels. Battery electric trucks are roughly 10 years behind light duty EVs in terms of product adoption. Of course, Mike from NACFE mentioned the S-curve this morning. So yeah, roughly 10 years behind light duty EVs. And long haul is not here yet. But bear with me, guys, this is a bold statement. I will go into more details. I would dare to say that in the next decade, it will be made possible without much effort or naturally. You'll get to see why I put out that statement. So Class 8 trucks are currently delivered with 350 to 600 kilowatt hours batteries. They require 150 to 250 kilowatt hours per 100 kilometer range. So this can yield with a payload in a 250 to 450 kilometer range. Of course, this is not enough without charging to be used on a long haul scheme. Current max charging powers are approximately 150 up to 250 kilowatts for some trucks. So today it would not be sufficient, or it would be kind of hard and would require a big shift in operations to be used in long haul again. Charging times for 800 for 80% state of charge are roughly, it always depends on multiple factors, but roughly about 60 to 120 minutes. So payload and elevation gain have a major impact on range. Payload is affected by battery weight. A few people mentioned this this morning already. But it's important to note, though, that clearly not everyone operates at max payload. There are a lot of fleets that operate in scenarios where we say they are cubing out. So cubing out means the cargo is limited by the volume taken in the box instead of in the trailer instead of the weight. So cubing out applications, of course, is a really good low-hanging fruit for EVs because yes, there is a payload penalty associated with the battery mass. You take this 80,000 pounds limit, and then you have to subtract a certain mass for the battery. I'll go into an example later in the slides. There's about 4,000 pounds penalty that depends on a bunch of factors, but we are talking about a 3% reduction in payload. But my note is that not everyone operates at max payload. And important to note as well, preliminary data that we have and that the OEMs have shared with us shows that winter does not affect range nearly as much as in light-duty EVs. I don't want to say at all that it does not affect, that there's no effect, but the battery sizes being way bigger than in light-duty EVs and the cabin being smaller in comparison to the rest of the truck body. In comparison, we don't see that typical 40% range decrease in our cold winter for trucks as we see in the light-duty EVs. Of course, as everyone, we are really eager to get our first data that comes from us, from our research center. Next winter, we will operate ourselves heavy-duty trucks, so we will be able to share with the world our data that we have coming from our cold winters in Quebec. But so far, what we have is the specs from OEMs and our modelizations, and yes, it shows that the winter does not affect range as much as in light-duty EVs. Especially because of the, you can precondition the battery while it's on the charger, precondition the cabin, and then leave for the day. And that really helps with the range. And another reason is that when the trucks come back to the depot for an opportunity charge, the batteries are still heating up. So all day, if they operate on a full day shift, the truck will be heated, and the big battery mass really helps with the thermal inertia And so that's a thing that's different when you compare it to light duty EVs. So future specs. I took this source from NACFE. I really love what NACFE is doing as far as visualizations and reports that they publish periodically. So big kudos to you, Mike, if you're still there. Thanks to NACFE for this. It dates a bit, so it's a 5-year-old figure that I put there in my slides. But still, I think that it's relevant. If you have the chance to look up the report, it's really, really good by NACFE. So it shows the parity. The parity is going to come on different topics concerning battery electric vehicles compared to diesel trucks. So the big topic is the battery energy density. It's progressing fast, though. I have a curve in the next slides. So of course that's affecting the payload penalty. If the energy density goes up, the payload penalty goes down, and this factor is currently progressing really fast. Another leap that's to have an eye on in the next years is the megawatt charging system. I don't know if you guys have heard about that one. The MCS has been released last year in Norway. It's currently still at the discussion phase, so it's not yet finalized, but it's the new charging standard or charging port, the mechanical interface, and the communication protocol that's going to allow for more than a megawatt charging power. So the current standard for the last decade in light duty EVs has been 50 kilowatts. As I mentioned earlier, for trucks currently 150 kilowatts. So that's an order of magnitude bigger. Of course, this is going to come at a really, really high price, in my opinion. Just to give you a rough estimate, a single house in the province of Quebec here might ask for 15 kilowatts of power. And so this is the equivalent of powering a small neighborhood of 60 houses for one charging station and one truck being charged. So it's really, really high power. It's not going to be easy to deploy. So I would not rely solely on that for the long haul. Yeah, next slide. There are two ways to charge battery electric heavy duty trucks. Of course, it's fleet operated chargers or public chargers. So fleet operated chargers, I want to go through that quickly. They come at a relatively high cost. We have put an anonymous figure that you can see at the bottom of the slide, just to give you rough estimates. That's in CAD, so Canadian dollars, of the pricing of a single charging station in function of the charging power. So yes, a single charging station could cost as much as a light duty car for a fleet. It is high cost. It is high cost to buy, to deploy, and then later on to operate on a daily basis, because demand charges are also significant. They have to be considered. That's dollars per kilowatts. So installation may require to own the building. That's a limitation. It is now easy to find resources, though, to help in the procurement and installation process for the EV charging infrastructure. Most trucks will require DC-FC charging stations, so fast charging stations. And the software to manage EV operations are on the rise. Privately owned stations may be used for opportunity charges, as you see at the bottom right. If you have privately owned chargers, you can use them within the day, within the shift, if you come back at the depot to get just a bit of a charge. So that can allow for more kilometers in a day. That's allowed by one charge on the truck. The other way to charge heavy-duty trucks, battery electric heavy-duty trucks, is, of course, the public or shared charging stations. Multiple startup, pilot projects, and shared station hubs are currently underway, both from public charging networks or private fleets. There is a strong will currently. There's really vivid discussions around who's going to deploy the first hubs in Quebec or elsewhere in North America. So on the left, you see a pilot site that the Hydro-Quebec have put up. This is by Circuit Electric, which is our utility-owned charging network in Quebec. So this is in Laval, North Shore of Montreal. It's one of the first stations where there's a drive-through configuration that allows for trucks to charge. There's a 350 kilowatt ABB charging station there as well that's being tested. So that would be publicly funded with a public network. On the far right, you see What EV, a render that they put out a few months back. What EV is on the private side. So this is a startup that aims to deploy private charging hubs with a membership structure, and it's currently under construction phase. I believe it's in California, that site. And in the middle, you see a really, really interesting scheme. It's a half and half. So it's both private and both public charging location that's in Portland, Oregon. It was paid by Daimler Trucks North America and Portland General Electric. And yes, it is me on that picture. I went there to visit last May. So really quickly, the SWOT.
Yeah, if
Frank-
you can wrap up in 1 minute, Charles, please.
1 minute. All right. So BEV trucks are already on the road. Upfront costs are no longer a big issue, as many people covered the subsidies this morning. The subsidies cover almost all of the cost difference, and they can cover pilot project, internal hours, and consultancy if applicable. Public stations are coming. Private stations now are broadly covered topic. Charging is easy. That's a sentence I stole from NACFI. Again, kudos, Mike. Park, plug, confirm charging, and go home. And the vehicle architecture is quite simple. Weaknesses: charging time is the main hurdle, of course. We spoke about that. No matter the ROI of a charging solution as a whole, even though you account for the driver waiting, people expect the same refueling time, which is about 15 minutes as for diesel. The payload penalty is about 4,000 pounds, as we mentioned. Chargers are new assets to manage and maintain. Demand charges, so that's dollars per kilowatt of charging, are considerable, as I mentioned. And there's a steep learning curve for managing large EV fleets. Opportunities: I spoke about public and shared charging stations that are coming. Battery density is on the rise, so that will reduce the payload penalty. Battery prices are getting lower and lower, and the grid is getting cleaner every year. Now the threats: there is a lot of misinformation about EVs, leading to a slower adoption. Someone else mentioned that there's a lot of noise and marketing around that topic, so people are always expecting the next leap in technology to be right around the corner, so that slows down the adoption. We are very dependent on the battery supply chain. Labor shortage is currently the biggest pain for fleet operators, so that might slow down the adoption of any new technologies. And long haul is not the low-hanging fruit for OEM. They are currently focusing more on regional haul because this application works and there's a lot of money to be made. In the province of Quebec alone, 44% of fleet operators from class 6 to class 8 operate within regional haul. So nearly half of the fleets here operate on regional haul, and the technology already works. So this is the low-hanging fruit for OEMs. I will skip on the recommendations. We will have access to my PowerPoints in respect for the schedule. Again, thank you all. And if you want to visit our website, ivisolutions.ca, for our research center, and for our heavy-duty trucks demonstration project, it's the plug-in fleet project.ca. Thank you all.